Today we are looking at the Cape Pure Math Unit 2 2021 paper. So let us get right into it. Question 1. Two complex numbers are given as z subscript 1 root 5 over 3 plus root 5i, and we have a z2 2 minus 2i. Show that the complex number z1 over z2 is equal to root 5 over 6 e to the i 7 pi over 12. Okay, so the first thing we need to do is work out the modulus and the argument of each complex number. Let's begin with z1. So the modulus of z1 is square root of the real part square. Now the real part is root 5 over 3 square plus the imaginary part square, which would be root 5 all square. So we end up with root 5 upon 3 square is 5/3 plus root 5 all square is 5. So we can simplify, we can put everything over the denominator of 3. So this is 5 over 3 plus 5 over 1. So multiply by 3. We end up with 15 over 3. So this becomes root 20 over 3. And of course we can simplify this as root 20. So root 20 is root 4 times root 5, so we can rewrite it as that. And root 4 is 2, so this is 2 root 5 over 3. Now for z1, the modulus of z1, let's find the modulus of z1. z2, sorry, the modulus of z2. Just remind ourselves what z2 is. z2 is 2 minus 2i. So the real part square is 4. And the imaginary part square is also 4. So let's take an extra step here. Modulus of z2. So it's square root of 2 square plus 2 square. So we end up with root 8. So the modulus of z2 is root 8. And we can rewrite root 8 as root 4 times root 2, which is equal to 2 root 2. Now let's find out the argument of each complex number. So the argument of, begin with z1. So the argument of z1 is equal to tan inverse the real part square. So the imaginary part, which is root 5 divided by the real part, which is root 5/3. Alright, we can do some simplification here. So what we really have is root 5 divided by root 5 upon root 3. So we can rewrite that as root 5 times root 3 upon root 5. Root 5 into itself 1. So it just becomes tan inverse root 3. And tan inverse root 3, what's that? Tan inverse root 3, that's 60 degrees. That's 60 degrees. Or if you convert that to radians, multiply by pi over 180 to convert to radians. So that's pi over 3 radians. So that's the argument of z1. Let's now find the argument of z2. Now for the argument of z2, so the argument of z2 again is tan inverse imaginary over real. So the imaginary here is negative 2 over 2. And we'll end up with negative pi over 4. So let's call this theta 2. And let's call the argument of z1 theta 1. So based on what we're asked to show here, we need to rewrite each of them in the exponential form. z1 over z2. So let's do this. So now Z1 over Z2. So recall that the radius of Z2 is 2 root 2. We have it here, the radius of Z2 the radius of Z2 was 2 root 5 over 3. Radius of Z1, sorry. The radius of Z1, here it is. I'm going to separate it. So the radius of Z1 was 2 times root 5 over 3. E to the I, and theta 1, that's the argument of Z1. We found it to be pi over 3. Over, and the radius of Z2, we have it here, was 2 root 2. E to the I, and the argument of Z2 we have as found to be negative pi over 4. Right, so recall that the exponential form is r e I theta. All right, so we found we have r for each number and we have theta for each number. So let's do the division now. So 2 into itself, that's 2, and root 5 over 3 divided by root 2 would be root 5 over 6. And then you know the law indices, e. So we're subtracting the powers here, so we have pi over 3 minus, so dividing, same base e, so minus pi over 4. So it becomes pi over 3 plus pi over 4, which will work out to 7 pi over 12 times I, of course. Now that's for 1a. Part 2 of 1a, without using a calculator, determine the value of Z1 over Z2 all square. Alright, so let's remind ourselves what Z1 over Z2 was. Z1 over Z2 was root 5 over 6, root 5 over 6, e to the I, 7 pi over 12. And we are squaring that. So Z1 over Z2, and now we're going to square that. So we square the root 5 over 6, this becomes 5 over 6. Root 5 over 6 times itself is 5 over 6. And we know the law indices, we can simply multiply the powers. So this will be 2 times 7 pi over 12. 2 into 12 is 6, so is 7 pi over 6. And we can write this into the polar form. R is 5 over 6 cos theta, and theta is 7 pi over 6 plus I sine 7 pi over 6. Now we can use our calculator. So this is 5 over 6, and the cos of 7 pi over 6, that's negative root 3 over 2. And sine 7 pi over 6, that's negative half. And to do this, of course, you can put your calculator in radian mode, or you can convert to degrees and do the calculation. All right, so we can factor out. We can factor out minus half. So if I factor out minus half, I'll end up with minus 512 outside here. In the bracket, I'll have minus root 3. Sorry, positive root 3. Plus I. So we're at 1b. 1 root of a quadratic equation is given as 4 minus 7i. Determine the quadratic equation with real coefficients and has the root 4 minus 7i. So if 1 root is 4 minus 7i, then the other root will be the conjugate, which is 4 plus 7i. So one root is, let me call one root z, we'll call it z, equal to 4 minus 7i. So the other root would be z equal to 4, the conjugate, which is 4 plus 7i, which means that z minus 4 plus 7i, so group everything on one side, would be equal to 0, or on the other side, group everything on the other side, z minus 4 minus 7i would be equal to 0, which means that z minus 4 plus 7i into z minus 4 minus 7i should be equal to 0. Alright, since either of those expressions are 0, then the product must be equal to 0. Since either of them is 0. Let's do the expansion. So let's take the z and expand to all 3 terms in the second bracket. So z times z, that's z squared. Z times minus 4, that's minus 4z. And z times minus 7i, that's minus 7zi. I'll take the negative 4 and do the same thing, distribute to all the terms in the second bracket. So minus 4 times z, that's minus 4z. And minus 4 times minus 4, that's positive 16. And minus 4 times positive 7i, that's minus 4 times negative 7i, sorry, that's positive 28i. Then I do the same thing with the 7i. So 7i times z, that's positive 7zi. Positive 7zi. And then 7i times minus 4, that's minus 28i. And 7i times minus 7i, that's minus 49i squared. And that is equal to 0. Let's see if we can group some like terms now. So we have z squared, that's the only z squared term there. So we have z squared. So what else do we have? So notice here we have minus 4z. So we have minus 4z, that's minus 8z. What else we have? We have z squared. What else we have? We have negative 72i. We'll cancel with positive 72i. Alright. What else we have? We have negative 28i. We'll cancel positive 28i. So what we have remaining is 16, positive 16, minus 49 I squared. Now I squared is negative 1. So rewrite I squared as negative 1 equal to 0. So this becomes z squared minus 8z plus 16, and then minus 49 times minus 1, that's positive 49 equal to 0. So this becomes z squared minus 8z, and 16 plus 49, that's positive 56 equals 0. So that would be our quadratic equation. Let's move on to the next question. Show that the derivative of sine inverse cos x over 1 plus sine x with respect to is equal to, and they gave us an expression there. So we're going to let y be equal to sine inverse cos x over 1 plus sine x. Alright? So we can let u be equal to cos x over 1 plus sine x, and let us find u. Differentiate cos, we get minus sine, so that's minus sine x into the denominator, which is 1 plus sine x. Apply quotient rule, and quotient rule now. Now we're going to differentiate the denominator. We get cos x, and then we multiply it to the numerator, which is also cos x. So now we can expand the bracket. We divide the numerator. I will divide everything by the square of the denominator, which is 1 plus sine x all square. So let's try and simplify the numerator. So this is u prime equal to, let's expand. So we have minus sine times 1, that's minus sine x. Minus sine times sine, that's minus sine square x. And then minus cos times cos, that's minus cos square x, all over 1 plus sine x all square. So let us continue. So this is u prime is equal to, now, so we have minus sine x, and we can factor out minus 1 here. So we have minus 1 in the bracket. We have sine square x plus cos square x. So well-known identity. We know that's equal to 1. So in the bracket we have sine square plus cos square all over. Let's restate the denominator in each line. All over 1 plus sine x all square. So this means that u prime will be equal to minus sine x minus 1 over 1 plus, because what's in the bracket, sine square plus cos square, all that will equate to 1, right? So in the bracket below we have 1 plus sine x all square. And if we factor out 1 again in the numerator, we'd have minus 1 into 1 plus sine x. In the denominator, 1 plus sine x all square. So we have 1 plus sine x into itself. So it's negative 1 over 1 plus sine x. So u prime is negative 1 over, since 1 plus sine x up here, we'll cancel one of this. So we'll have negative 1 over 1 plus sine x. Now, in terms of the rule for differentiation, remember the rule for differentiating inverse trig function. Alright, so remember the rule here is u prime over root 1 minus u square. Alright, so the derivative, so dy, so remind yourself what y was. So y was this, sine inverse u. So dy by dx would be u prime. Let's write it. So dy by dx would be, let me just write it proper. For inverse trig function, sine inverse u, dy by dx is u prime over root 1 minus u square, which is equal to, so we just found u prime to be negative 1 over 1 plus sine x. That's u prime. And that's into now root 1 minus u square. So that's root 1 minus u square. And remind us, what was u? So u was cos x over 1 plus sine x. So that's cos x over 1 plus sine x all square. So that's cos x. Let me just move it from there. So let me just put it down below here. So what we have here is u prime, negative 1 over 1 plus sine x, here into root 1 minus u square. And again, what was u again? U was cos x over 1 plus sine x. So cos x over 1 plus sine x all square. So cos x over 1 plus sine x all squared. So we need to simplify this and show that we'll end up with what they asked us to prove is equal to this expression here. Let's try and fix it up now. Alright, so a little trick we could use is to rewrite the 1 plus sin x as root 1 plus sin x all squared. So remember, for example, x, we can write x as root x squared. Alright, same idea. So we square it and then root it. Alright, and then now, of course, so below we have root 1 plus sin x all squared times root the other bracket. We'll end up with negative 1 over, now root 1 plus sin x squared times 1. That's 1 plus sin x squared. That's root. So it's 1 root. So remember, root a times root b is root ab, right? So we can 1 square root umbrella and take the product of what we have beneath the root there. So 1 plus sin x all squared times 1. That's 1 plus sin x all squared. And 1 plus sin x squared times that. 1 plus sin x cancel. Alright, so we're left with just minus cos x all squared. And therefore now let's continue. 1 plus sin x all squared, we can expand. Actually, we don't need to expand. That's what we're asked to prove, right? That's what we're asked to prove. Alright. Now this part, you're probably wondering how we arrive at 1 plus sin x all squared times this bracket here. So remember, if a squared times b squared is, we can take the product of a and b and the 1 square, right? One of the laws are indices. So we have 1 plus sin x squared. In the second bracket here, we have 1 over 1 plus sin x all squared also. So we can take the product of these two terms in the bracket times this other term. And of course, we'll be left with just cos x all squared, since 1 plus sin x into itself would be 1. Alright, let's move on to the next question. A curve is defined parametrically as x equal 3 minus 2t all squared, y equal t cube minus 2t. Determine the equation of the tangent at the point where t equal to 2. So we have x equal to 3 minus 2t all squared, which means that dx by dt, I'm going to use chain rule. So multiply by the power, so 3 minus 2t all to the power of 1, and of course I differentiate the terms in the bracket. I end up with minus 2. So this becomes minus 4 into 3 minus 2t. If I expand the bracket, I get minus 12 plus 80. Or let me put the 80 at the front. It looks neater that way. 80 minus 12. And let me also find dy by dt. Now y is t cube minus 2t. Therefore, dy by dt is 3t squared minus 2. So now dy by dx, so therefore remember that dy by dx is dy by dt divided by dx by dt. Alright, so dy by dx is dy over dt divided by dx over dt, which means that dy by dx is what's dy by dt. dy by dt is 3t squared minus 2 over, and what's dx by dt? 8t minus 12. Let's continue. So we want the gradient when t is 2. So we can substitute t equal to 2 into dy by dx. So when t equal to 2, when t is equal to 2, then dy by dx is 3 times 2 square. So it's 3 times 2 square minus 2 over 8 times 2 minus 12. So we end up with, so 3 times 2 square. So 3 times 4, that's 12. 12 minus 2, that's 10. Over 8 times 2, that's, actually this is 12. So it's minus 12. So 8 times 2, 16. 16 minus 12, that's 4. So can reduce it to 5 over 2. So this is what the gradient is, or we can call it m. All right, the gradient for the tangent. Now we need a point on the function, so we can use this. Now notice when t is 2, we can get an x coordinate. When t is 2, x equal to, I can replace, if I put 2 for this is 3 minus, x is 3 minus 4. 3 minus 4 to the power of 2. And then y would be, the y here would be, if I replace 2 in this, so 2 cube, this is t cube, so 2 cube would be, so 2 cube minus 2 times 2. So the x would be positive 1, because negative 1 all squared, that's positive 1. And the y would be 2 cube, which is 8. 8 minus 4, that's 4. So the function passes through the point when x is 1, y is 4. So it's passed through the point 1, 4. Right, so it passes through the point 1, 4. Good, so the equation, so therefore, equation of, so of course we can multiply. Alright, that's kind of so cross multiply there. So we end up with 2y minus 8, so 2 times y, 2 times minus 4, equal to 5x minus 5. I can just group some like terms out, so 2y equal to 5x. If I add 8 to both sides, I end up with negative 5 plus 8. That's positive 3. So that's the equation for the tangent. Anything like this or equivalent to this should be okay. Question 2. Using the substitution e to the x equal 3 cos theta, or otherwise determine the integral of e to the x root 9 minus e to the 2x dx, and we're going to use the substitution e to the x equal 3 cos theta. Now, one thing we can do is we can log both sides. So let me just log both sides. So log e to the x equal ln 3 cos theta. So I log both sides. So ln e to x is x log e. And we know log e is 1, right? So x equal to ln in the bracket 3 cos theta. So we can find dx by d theta. Differentiate a log, we differentiate what's in the bracket. So with minus 3 sine theta over what's already in the bracket, which is positive 3 cos theta, and minus 3 into itself was minus 1. So we end up with just minus sine theta over cos theta. Of course, this is dx by d theta. So we can transpose for dx here. So if we can multiply both sides by d theta, so dx would be equal to minus sine theta over cos theta times d theta. We can substitute all of that now into this. So therefore, continuing here, it's integral of e to the x. Now e to the x, so we're using 3 cos theta root, let me separate this, root 9 minus e to the 2x. Now e to the 2x will be the square. So e to the x is 3 cos theta, which means e to the 2x, I just square both sides, so get e to the 2x. Alright, square both of this side. So e to the 2x will be 9 cos square. And dx by theta will be minus sine theta over cos theta times d theta. Alright, let us continue. So this is integral of 3 cos theta, let's repeat that, square root, and this is 9 into, factor out the 9, that's 9 into 1 minus cos square theta. And then outside here, we have minus sine theta over cos theta d theta. Continuing. So this is the integral of 3 cos theta. So of course I can factor out 9 root 9. So I can factor out root 9. If I factor out root 9, I end up with 3. So this is cos theta times root 9. Factor out root 9. And then I'm left with root 1 minus cos square. But remember, 1 minus cos square is equivalent to sine square. Alright, remember 1 minus cos square is equivalent to sine square. So and then I have to repeat my minus sine theta over cos theta d theta. So continuing. Alright, let's continue. What happened now? Cos theta into itself, that's 0. That's 1, sorry. Alright, so we're left with 3 times root 9. Root 9 is 3, so 3 is 9, so I end up with 9. And then root of sine square is sine. So this is sine theta times minus sine theta, we have left there, d theta. Alright, continuing. So this is root integral of 9 minus, so minus 9 sine square. Sine times sine is sine square, d theta. Now you recall that the double angle, cos, recall, let's put it over here, recall that cos 2 theta is 1 minus 2 sine square theta. So I can transpose a sine square, so I mean 2 sine square theta is equal to 1 minus cos 2 theta. Divide both sides by 2. So sine square theta is 1 minus cos 2 theta over 2. So this would be equal to integral, and I'm going to rewrite the sine square theta as 1 minus cos 2 theta over 2 d theta. And of course I can factor out minus 9 over 2. So minus 9 over 2 into 1 minus cos 2 theta d theta. Now I can integrate now. So minus 9 over 2. Alright, integrate 1 with respect to theta. I end up with theta, and integrate cos 2 theta. I get what? Minus sine 2 theta over 2. So now this becomes minus 9 over 2. No, what is theta? Let's put it back in terms of x. Now remember that e to the x was equal to 3 cos theta. Let me just put it down here. Remember, e to the x was equal to 3 cos theta, which means that e to the x, divide both sides by 3, e to the x over 3 would be equal to cos theta, which means that theta would be cos inverse theta. From here, theta would be cos inverse e to the x over 3. So theta, replace theta with cos inverse e to the x over 3 minus Alright, so let's look at sine 2. So remember sine 2 theta, sine 2 theta, sine 2 theta is 2 sine theta cos theta. Alright, sine 2 theta is 2 sine theta cos 2 theta. So sine 2 theta over 2 would be just sine theta cos theta. So it'd be sine theta times cos theta. But we know cos theta is e to the x over 3. So e to the x over 3. So replaced. Let me just do it step by step. Let me delete that and do it step by step. So sine 2 theta over 2 from a double angle, this is equal to sine theta cos theta. Now remember, we want to get rid of all the theta terms, replace them with x terms, right? So let's take an extra step here. So this becomes minus 9 over 2 cos inverse e to the x over 3 minus sine theta cos theta. Now we know cos theta is e to the x over 3. So the cos theta part here is e to the x over 3. That's the cos theta. Now let's what's the sine theta? Now sine theta, remember that sine square is equal to 1 minus cos square theta. So sine theta is equal to the square root of 1 minus cos square theta. So the sine theta, I can replace the sine theta with the square root of 1 minus cos square. So the sine theta is square root of 1 minus cos square. What is cos square? Now cos is e to the x over 3. So cos square this will be e to the 2x over 9. So it will be e to the 2x over 9. And that would be our integral. And of course it's indefinite integral, so don't forget the plus c. Alright, let's move on. Use partial fractions to prove that. And we have an expression here. Use partial fractions to prove that. So let's jump into it. Now, based on the factors that give us in the denominator here on the right hand side, let's just ensure that these are really factors of the cubic polynomial here in the denominator on the left hand side. So let just check it. So let f of x be equal to 2x cubed minus x squared plus 8x minus 4. Based on this, it says that f of half, so 2x minus 1 equals 0, which means x equal to a half. So basically saying that f of half should give us 0 since 2x minus 1 is a factor. Let's find f of half. Just to ensure f of half will be 2 times half cube, replacing x with a half, minus half square plus 8 times half minus 4. So half cube is 1/8, so 2 times 1/8, that's a quarter, minus half square, that's also a quarter, 8 times a half, that's 4, minus 4. So f of half is a 0. So we know that 2x minus 1 is a factor. Let us get the other factors now, so we can use long division to get the other factors. So let's use long division to get the other factors. So I'm going to divide 2x minus 1 into the function. So we have 2x cubed minus x squared plus 8x minus 4. So 2x into 2x cubed, that's x squared. Alright, so x squared times the divisor, we get 2x cubed minus x squared. Of course, we subtract, we get 0, 0, 0, so 0, so we bring down the 8x. Alright, so 2x into 8x, that's 4. So 8x bring down negative 4 also. So 4 times 2x minus 1 That's 8x minus 4. And of course, if we subtract, we end up with 0. All right, so we know that we are confident now that 2x minus 1 and x squared plus 4 are the factors of the denominator here and the left hand side. All right, so we can let's restate it. 2x plus 1 over the function over the function 2x cubed minus x squared plus 8x minus 4 is equal to, all right, let's call it a over 2x minus 1 plus, let's call it bx plus c over the other factor, bx plus c over x squared plus 4. Now our job is to find the value of a, b, and c. So one thing we can do is make everything under one common denominator. So we can rewrite this as 2x plus 1 over 2x cubed minus x squared plus 8x minus 4 equal to, and we can bring everything here under over a common denominator, 2x minus 1 times x squared plus 4, and that was what now? A times x squared plus 4 plus multiply, that's 2x minus 1 into bx plus c. Good. So since we have same denominator, we can just drop the denominators, and the left hand side 2x plus 1 is equal to a to x squared plus 4 plus 2x minus 1 into bx plus c. So now we can let x be equal to a half. If x is equal to a half, on the left hand side we end up with 2 times a half plus 1 equal to half a into half square, that's quarter plus 4. Let's solve for a now. So 2 times a half, that's 1 and 1, 2, and equal to 4 and a quarter. So 4 and a quarter, what's that now? 17 over 4. Alright, so to get the value of a, we can multiply both sides by 4 over 17. So multiply both sides by 4 over 17. 4 over 17 times its reciprocal on the right is 8. And then this is 2 times 4 over 17. That's 8 over 17. So the value of a is 8 over 17. Let's try to get the other values. We can also let x be as small number as possible. Let x be 0. If x is 0, the left hand side will be just 1. Over here on the right hand side, if x is 0, this bracket will be 0. So we'll end up with 4a. If x is 0, this bracket will be just minus 1. And then this bracket will be just c. So we have minus 1 in this bracket and just c. So we'll end up with just minus c. Now we know the value of a is 8 over 17. So 1 equal to 4 times a, which is 8 over 17 minus c. So we can do some transposing here, which means that c would be equal to 4 times 8 is what? 32. 32 over 17 minus 1. So c would be, so that's 32 over 17 minus 17 over 17. That's what? 15 over 17. So c is 15 over 17. So we have values of a and c. we now also need the value of b. So this time we can let x be equal to 1. Alright, and the same thing, let x be equal to 1. So on the left hand side, if x is 1, alright, so remember we're using this now. Let x be 0, we're using this. Let x be half, we're using this. Now we're letting x be equal to 1. So if x is 1, on the left hand side, 2 times 1 plus 1, that's 3. Equal to, if x is 1, we would have 1 square plus 4, that's 5, so that's 5a. If x is 1, in the first bracket here would be just 1. 2 times 1 minus 1, so that's 1. And if x is 1, it's just b plus c. So we end up with just b plus c. So plus b plus c. Remember, we're solving for b, right? So we're solving for b, so therefore it's 3 minus 5a minus c is equal to b. Alright, so I'll leave the b on one side, group everything else on the left hand side. So 3 minus 5, now a, remember a is 5 or 8 over 17. So 5a will be 5 times 8 over 17. Minus c, and c is 15 over 17. So I can use my calculator to perform all of those calculations. I can write 3 over 1, 17 times 3, over 17 times 1. Alright, so 3 times 17, that's what, 51. So that's 51, equal b. So that's 3 times 17, 51. 5 times 8, 40. Minus 15. So that's 51. Minus 55. That's what, negative 4 over 17. So b is negative 4 over 17. Which means the proof is done. Alright, so this proof is done. So now we can write 2x plus 1. So now it means therefore. So therefore 2x plus 1 over 2x cubed minus x squared plus 8x minus 4 is equal to, now we had said it's a over 2x minus 1 plus bx plus c over over x squared plus 4. So a, we just found a to be, I jumped in the gun there a while ago. So we just found a to be 8 over 17. So replace a with 8 over 17. So 8 over 17, 2x minus 1. And so remember now b and c are both over 17. Alright, and b was negative 4. There it is, so we can write it as negative 4x over 17 x squared plus 4. And the value of c was 15 over 17. So when you're writing, you actually put minus 15, because when you expand and distribute the negative here, minus, so it's minus become positive 15. Alright, so it's proven. Let's move on to the next question. Hence, find the integral of that. So, integral of 2x plus 1 over 2x cubed minus x squared plus 8x minus 4 dx. So, just put it in, so it's equal to the integral. Let's write the partial fractions now. 8 over 17, 2x minus 1 minus 4x minus 15 over 17 into x squared plus 4. And what we can do is separate it. Let's separate it. So we can write this as 8 over 17, 2x minus 1. Alright, let's separate these two numerators now. So minus 4x over 17x squared plus 4. And separate this. Plus 15 over 17 x squared plus 4. And we're integrating, of course, with respect to x, so dx. Alright? Which means that alright, the integral now, we can log the denominator. So we'll log 2x minus 1. Now, if you differentiate 2x minus 1, you will end up with 2 in the denominator. Alright, but remember you want 8, you actually want it 8 over 17. Alright, so this would be actually 4 over 17. Alright, so double check, because if you differentiate log 2x minus 1, you'll get 2 in the numerator, and the time the 4 to give you about the 8 up here. Alright, here, likewise, log the denominator, you get ln x squared plus 4. Differentiate x squared plus 4, you'll get 2x, but you actually want 4x. Right? So you have to multiply it by 2. And remember the 17 in the denominator here. Here. So of course we have 15 over 17. And of course is 1 over a quadratic. So we use the inverse. We differentiate using the inverse trig function tan, and the a would be 2. So we have 1 over a, so 1 over 2, tan inverse x over a. So tan inverse x over 2. Right? Plus your constant, of course. And of course you can always rewrite this as 15 over 34. Alright. So now we're on to question 3. Determine the third partial sum of the series. Alright, so we want the summation of the first 3 terms. Alright, so let's get the term by term. So I'm going to call the first term A1. So A1, to get the first term A1, I simply replace the k here with 1. So it's become 8 over 4 times 1 square minus 1, which will be what now? The first term would be what now? 8 over 4 minus 3, so that's 8 over 3. I'll get the second term, call it A2, by replacing the k with 2, so it'll be 8 over 4 times 2 square minus 1. So this becomes 8. Now 2 square is 4. 4, 16. 16 minus 1, 15. So the second term is 15. And the third term, I'm replacing now k now with 3. So it's 8 over 4 times 3 square minus 1. So the third term will be 8 over, now 3 square is 9. 9 times 4 is 36. 36 minus 1, that's 35. Alright? So the summation of the first 3 terms. So the summation of the first 3 terms is the first term is A3 plus second term 8 over 15 plus third term 8 over 35. And that would give me, the summation of the first 3 terms would give me actually 24 over 7. Just use your calculator to do those addition. Next. Show that the summation from k equal 1 to n is 8 over 4k squared minus 1 equal to 8n over 2n plus 1. So this I will use proof by induction. So so remember I have the first three terms. Remember the first term was, so to the left hand side, when k is 1, remember we got 8 over 3, plus when k is 2, remember we got, what was it, 8 over 15, and for the third term we got 8 over 35, plus, and the n term, I replace the k with n, so it will be 8, n term will be 8 over 4n square, minus 1, and this should be equal to 8n over n plus 1. So the formula on the right hand side gives us a summation of the first n terms. You will notice, remember the summation of the first n terms was, what was the summation? We end up with 24 over 27. Notice if you substitute 3 into this here, 8 times 3, you end up with 24. And you substitute 3 in the denominator, 2 times 3, 6 and 1, 7. So when you substitute n equal to 3, you get the summation of the first three terms, which we already know, 24 over 7. Alright, so it's just a straightforward proof by induction. Let's use proof by induction now to perform this proof. So proof by induction, 3 basic steps. So we're going to show true. So show true when n equal to 1. Now n equal to 1, notice the first term is 8 thirds. And the summation of the first term, replace n with 1. So 8 times 1, that's 8. Over 2 times 1, 2 plus 1, 3. Alright, so the summation for the first term is 8 over third. Same as the 8 over 3, same as the first term. So therefore, true for n equal to 1. Step 2, assume true when n equal to k. So this time we just go through and replace everything with k, right? So we have 8 third plus 8 over 15 plus 8 over 35 plus that, and the kth term will be 8 over 4k square minus 1. And of course, to get the summation for the first k terms, on the right hand side, replace n with k. So end up with 8k over 2 times k plus 1. That's step 3. Step 2. Step 3 now, and this is the most difficult step, to show true for when n equal to k plus 1. And to complete the step, to follow up from step 2, we're going to add one more term, the k plus 1 term. So again, we repeat it. So first term was 8 thirds. Second term is over 15 third, 8 over 35, plus that plus the kth term was 4 over k square minus 1 plus, and now we're going to add one more term. Now if you look at how we are getting the terms, so this time now we're going to replace now the k with k plus 1, because now the final term is k plus 1. So 4k square will come 4 times k plus 1 square. So it's 8 over 4 times k plus 1 square minus 1. So it's 8 over 4 times k plus 1 all square minus 1. And on the right hand side, we're summing up now k plus 1 term. So replace the k with k plus 1. So this is 8 times k plus 1. So we're summing, on the right hand side, we're summing k plus 1 terms, right? And then this is 2 times k plus 1 plus 1. And let me put a question sign there. Because the task now is to show that what we have on the left hand side is equal to what we have on the right hand side. So the left hand side is all of this. We want to show is equal to the right hand side. So notice now from step 2, from 8 over 3 to 8 over 4k square minus 1. Look at step 2. From 8 over 3 to 8 over 4k square minus 1. All of that is equal to 8k over 2k plus 1. All of that is equal to 8k over 2k plus 1 plus, and here we have 8, we have 8 over 4 into k plus 1 all square minus 1. Now we need to show that all of this will simplify to what we have on the right hand side here. So abbreviating left hand side is equal to that. Let's see if we can reduce it to what we have on the right hand side now. Alright, so now we have 8k over 2k plus 1 plus, now you'll notice in the denominator is actually a difference of 2 squares, alright? So notice a difference of 2 squares. So 4 square root of 4, and so 4 and this is 2 square, this is k plus 1 square. So we can just use a square bracket to separate it. So we have 2 into k plus 1, difference of squares, alright, minus 1. And then here we'd have the conjugate, which is 2 into k plus 1 plus 1. Alright, and I use a square bracket to separate it. Alright, so we end up with now, let's continue. So we end up with now 8k over 2k plus 1 plus 8 over, notice now in the first bracket here, this first square bracket here, if we expand, we'll get what? 2k plus 2, 2k plus 2 minus 1. So this will simplify to actually 2k plus 1. Because 2 times k is 2k, 2 times 1 is 2, take away 1. So we end up with 2k plus 1. And in the other bracket, we still have our 2 into k plus 1. 2 into k plus 1. Change that. 2 into k plus 1. Plus 1. Alright. So now notice we can ensure we have a common denominator here. So we have 2k plus 1. So what we could do is multiply this, multiply the first bracket here by, let me just extend it. Let me just this here. So notice over here, this is 2k plus 1. So what we can do is multiply this denominator by this square bracket here. Multiply by this square bracket here, so we end up with 2 into k plus 1 plus 1. But remember the whole idea of equivalent fraction. We have to multiply the numerator by the same thing. Which is 2 into k plus 1 plus 1. Alright, so now we have one denominator. So where can I put it now? We have one denominator. So this is equal to, so the one denominator is 2 k plus 1, 2 into k plus 1 plus 1 times 2k plus 1. So both of them are what we call like denominators, which means we can bring the numerators together. Alright? And of course, let's bring the numerators together. So in the bracket here, if I expand, I'll end up with 2k square. I end up with 2k square, 2k, end up with 2k plus 2 plus 1, 2k plus 2 plus 1, that's 2k plus 3. And outside I'll have 8k plus 8. Alright. Continuing now. I can expand the bracket. So in the numerator I'll have 8k times that, that's 16k square. 16k square plus 8k times 3, that's 24k plus 8 all over the denominator here, of 2 into k plus 1 plus 1 times 2k plus 1. Continuing. Of course, I can factor out the 8. So if I factor out the 8, I'll have 8 into 2k squared plus 3k plus 1 all over the denominator, which is 2 into k plus 1 into 2k plus 1. And notice in the quadratic there, in the numerator, the quadratic there, let's extend, just ignore this. Let's ignore this. Alright, continuing. So again, the denominator will remain the same. 2 into k plus 1 times 2k plus 1. Alright, in the numerator now is a quadratic. I can factorize. So the factors obviously will be k plus 1 and 2k plus 1. So this the numerator you can factorize there by itself. You end up with that. Notice 2k plus 1 into itself, that's 0. So we are left with 8. We are left with 8 into k plus 1 over 2 into k plus 1 plus 1. Let's check if that's what on the right hand side. 8 into k plus 1. So that's the proof. Alright, so 8 into k plus 1. And in the denominator, 2 into k plus 1 plus 1. Alright, so the proof is done. So therefore, true for n equal k plus 1. Hence, true for all n where n belong to the set of natural numbers. So the proof is done. Part B, determine the Taylor series expansion e to the cos x about x equal pi over 2 up to determine x cubed. Let's remind ourselves of what the formula for the Taylor series expansion is. So f of x, the formula is f of x is f of a. Of course, where a would be pi over 2, right? F of a plus f prime plus x minus a times f prime a plus x minus a square, second derivative evaluated at a, over 2 factorial plus third derivative a over 3 factorial x minus a cube plus that. Alright, so our job is to find out the first 3 derivatives. The first 3 derivatives, yes. Alright. So remember, remind ourselves, so f of x is equal to e to the cos x, as we are told. So let's use that and let's find f of a. So of course we're using a to be pi over 2. So f of a, of course, is f of pi over 2. Or 90 degrees is in degrees, or 19 degrees, right? So f of a will be e to the cos pi over 2. Now the value of cos pi over 2 is 0. So e to the 0 and e to the 0 is 1. Now let's get the first derivative. So f prime x is equal to, differentiate the power. we get minus sine x cos e to the cos x, so we'll leave the power alone. E to the cos x. And then we evaluate, we substitute now pi over 2 for the x, so f prime a. Now we're going to replace x with pi over 2, so sine pi over 2 e to the cos pi over 2. Now sine pi over 2 is negative 1. Alright, so it's negative 1 times 1, cos 90, we established that's 0. Cos pi over 2, that's 0, that's 0, so e2 is 0 is 1. So that's all of that will work out to be negative 1. Next, second derivative. So this, of course, we apply the product rule. So let's apply the product rule. So if I'm using the product rule, I'll differentiate negative sine x first. I'll get negative cos x. And then leave e to the cos x alone. Plus, and now I'll keep the negative sine x. I'll keep negative sine x. And then now I'll differentiate e to the cos x. Differentiate e to the cos x. I get negative sine x again. So negative sine, so I end up with plus sine square e to the cos x. And then now I find evaluate at a. Replace x with pi over 2. And I'll end up with, what will I end up with now? Alright, so cos 90, 0, all of this will become 0, cos 90 is 0. And sine 90 is 1, so I'll just end up with 1. And now let's find the third derivative now. So to get the third derivative, what I'll do first for the second, let me just rewrite the second derivative. I'm going to rewrite it by factoring out e to the cos x. So second derivative, let me factor out e to the cos x. And if I factor out e to the cos x, what I'll have is sine square x minus cos x. So I'll use a product rule to differentiate this. So the third derivative, I'll be using the product rule. So third derivative, differentiate. Let me differentiate the bracket first. Differentiate bracket first. So I'll keep the e to the cos x. Differentiate the bracket. I'll get 2 sine x cos x, because I would use a chain rule there. Differentiate minus cos x. I get positive sine x. Alright. Plus, and now I'm going to differentiate e to the cos x. I'll get minus sine x e to the cos x. And then I restate my sine square x minus cos x. And then for the x now, I'm going to replace x now with pi over 2. So I'm going to evaluate the third derivative at a. And remember, a was pi over 2. Radians are 90 degrees. So e to the cos 90, e to the cos pi over 2, that's 0. So it's e to the 0, so I'll have 1 outside the bracket there. In the bracket, cos 90 is cos pi over 2. I keep saying that cos pi, well, same cos 90 degrees, pi over 2 radians. And let me use 90. Cos 90, that's 0, so this will become 0. All of that will become 0. Plus, and sine 90 is 1. Minus, sine 90 is 1. So 1 e to the 0, so I have minus 1 outside here in the bracket. Sine 90 is 1, so 1 minus and cos 90 is 0. So I end up with that. So what I really have now is in the first bracket, so 1 times 1, which is 1. So everything becomes 0. Alright? So I have the first three derivatives evaluated at A. Alright, so what are they? So it was 1 minus 1, 1, 0. So I'm going to replace now. So let's do the substitutions now. Using the formula. So here's the formula. Let me put it up here. I want to do it while I'm looking at the formula. So the Taylor series will be f of x equal to f of a, f prime a here would be f prime a. Here's it. F of a, sorry, would be 1. So 1 plus x minus pi over 2, where a was pi over 2, f prime a, and f prime a was what? Negative 1. So I'll have negative 1 outside here, so I'm going to put negative 1. It's actually negative 1 plus x minus pi over 2, x minus pi over 2 square over 2 factorial, with 2 factorial is just 2, and the second derivative at a was 1, and it was 1, so 1, right? And the final term in x cube, third derivative at a was 0, so 0 x minus pi over 2 all cube over 3 factorial, which was 6. So those will be the first three terms up to x cube. Let's move on next. We're asked to use the series expansion to approximate e to the cos pi correct to 2 decimal places. So e to the cos pi. So this time we're going to replace x with pi. We're going to replace the x value with pi. Alright, so e to the cos pi equal to, so we're going to come back to the Taylor series expansion, and we're going to replace now all the x terms with pi. So this would be 1 minus bracket pi minus pi over 2, and the other one half pi minus pi over 2 all squared. 0 times that will be 0, so we won't be using this, the fourth one. So it's 1 minus pi minus pi over 2 plus pi minus pi over 2 all square over 2. Well, alright, so this will be now 1 minus pi over 2 plus pi minus pi over 2 all square over 2 over the 2 factorial, which was 2. Alright, and of course we can use our calculator for this. So this is 1 minus pi over 1 minus pi over 2, that's pi over 2. Alright, and this is pi. This is pi minus pi over 2, so that's half pi all square. That's pi over 4 divided by 2. Pi square over 4 divided by 2, that's pi square over 8. And of course we can use our calculator, replacing pi with 3.14, and I'm getting 0.66245 when I'm using pi to be 3.14, but 2 decimal places. So 0.66. 0.66 to 2 decimal places. So part C, the first and fifth terms of a GP are 16 and 9 respectively. Determine the third term of the projection. So the first term, you can call A is equal to 16, and the fifth term, so AR to the power of 4 would be equal to, the fifth term is 9. Alright, so our job is to find the third term. So of course we can use this to calculate. R. So replace A with 16. So this would mean that from here, this would mean that A is 16. So 16 times R to the power of 4 would be equal to 9, which means that for the square root of both sides, 4R square would be equal to 3. So R square would be 3/4. Now the third term is actually equal to AR square. So remember the first term is A, second term AR, third term AR square, which is what we want, right? So the third term will be AR square. We know A to be 16, and we know R square to be 3/4. So 16 times 3/4, 4 into 16, 4 times 3, 12. So the third term is actually 12.